Today, we're unlocking the secrets of this. Well, this everyday superpower that completely surrounds us. It powers our entire world, and yet it remains totally invisible to the naked eye. Think about it. We flip a switch, boom, a room lights up. We plug in a phone, it instantly comes to life. But how often do you actually stop to visualize what's really happening behind the drywall? Today, we're going to demystify electricity by mapping it out step by step. To really wrap our heads around this, we have to start by asking the most fundamental question. What actually constitutes electricity? Like, literally, what is physically flowing inside our wires, our devices, our appliances? To answer that, we're going to embark on a little journey down what I like to call the invisible river.
Okay, so the absolute bedrock of our invisible river is something called electric current. Simply put, electric current is the rate of flow of electric charges through a conductor over a period of time. Now, there's a super fascinating historical quirk right here. You see, when the phenomenon of electricity was first observed, electrons hadn't even been discovered yet. Crazy, right? Because of that, early scientists just assumed it was a flow of positive charges. So out of pure convention, we actually still draw electric current as flowing from positive to negative. But in reality, in the metallic wires of our actual circuits, it is actually the negatively charged electrons doing all the heavy lifting, flowing in the exact opposite direction.
All right, let's take a quick look at the syllabus for today. We'll be looking at current and the circuit, voltage, the rules of resistance, decoding Ohm's law, and then finally, combining resistors in series.
So moving right along to section 1, current and the circuit, the basic flow of charges. Let's start with the baseline flow of charges that establishes an active electrical pathway. Listen, without a continuous and closed path, which is what we call an electric circuit, the current just stops dead in its tracks. If a switch gets turned off, that conducting link is broken and our river instantly runs dry. Now, when we actually want to measure this river, we obviously don't count individual electrons. They're just incredibly tiny. Instead, we use a unit of charge called a Coulomb. And to put that into perspective, just one single Coulomb represents the charge of nearly 6 quintillion electrons. That is a massive number. When we measure the rate of this massive flow, we use the Ampere, named after the brilliant French scientist André-Marie Ampere. Mathematically speaking, 1 ampere is simply 1 Coulomb of charge passing by a specific point every single second. It's really just a pure, straightforward measure of flow rate.
Okay, let's jump to section 2, voltage, the electric push, driving the current.
So, charges don't just decide to get up and move on their own. They really need a reason to go. Think about a perfectly horizontal tube filled with water. The water doesn't just spontaneously start gushing out one end, right? But if you connect one end to a water tank kept at a higher elevation, well, gravity creates a pressure difference, and the water flows. Electrons inside a copper wire act the exact same way. They need an electric pressure difference along the conductor in order to move. In electricity, we call this potential difference, and instead of gravity, it's generated by a power source, something like a battery. The absolutely crucial point here is that a battery cell actually expends its own internally stored chemical energy just to maintain this potential difference. Even when no current is being drawn at all, that potential is sitting there just waiting. And the very second it gets connected to a circuit, bam, that difference sets the charges into continuous motion. Formally speaking, potential difference is the amount of work done to move a unit charge from one point to another. We actually measure this electric push in volts, which was named after the Italian physicist Alessandro Volta. If we break down the formula we're looking at, 1 volt means exactly 1 joule of work is done to move 1 coulomb of charge between 2 points in the circuit. You can think of it as the ultimate measure of the energetic shove that gets given to our invisible river.
Which brings us nicely to section 3, the rules of resistance, slowing the river.
Every river faces obstacles, right? You've got rocks, sharp bends, narrow channels. As electrons travel, they aren't just cruising through empty space. No, they are actively, physically struggling against the atomic attraction of the atoms they're moving through. This resistance changes based on 3 key physical traits. First is the length of the conductor. The longer the wire, the more atoms the electrons have to fight through, so resistance goes up proportionally. Second is the cross-sectional area. A thicker wire actually gives the electrons way more room to flow, so the resistance goes down. And third is the fundamental nature of the material itself, which we call its electrical resistivity. This brings us to a pretty stark physical contrast. Materials with incredibly low resistivity, think of things like copper or silver, are pure conductors. They offer a super easy path and just let the river flow freely. But on the absolute opposite end of the spectrum, we have insulators, things like rubber or glass. Their resistivity values are astronomical. I mean, literally billions of times higher than conductors. They act as impassable dams, completely blocking the flow of the invisible river. All right, section 4.
Decoding Ohm's law, unifying the rules.
This is kind of the climax of the explainer, really, where we take our three core characters, current, voltage, and resistance, and we finally connect them together into a single predictable rule. But actually, before we look at the law itself, let's briefly establish the visual vocabulary of circuit diagrams so you can fluently read the scientific language we're about to see. We represent batteries with these alternating long and short lines for positive and negative terminals. Zigzag lines, those denote our resistors. And we have specific circular meters too. There's the ammeter to measure our river's flow, which is always connected right in the main path or in series. And then there's the voltmeter to measure the pressure difference, which is always connected in parallel right across the specific component we want to measure.
And this brilliantly illustrates exactly what the German physicist Georg Simon Ohm discovered way back in 1827. When you graph the voltage against the current for a given metallic wire, you get a perfectly straight line passing right through the origin. This proves definitively that current and voltage scale together proportionally, provided the temperature of the wire remains constant. Simply put, if you double the electric push, you exactly double the electric flow. So presenting Ohm's law in its most elegant mathematical form, we arrive at V equals I times R. Here, resistance, or R, is the exact constant of proportionality that links that electric push, V, to the electric flow, I. This one simple equation is truly the master key to almost all basic electrical engineering. If you know two of these values, you can always predict the third. Let's move to our final section, Section 5. Combining resistors in series, a single continuous path.
Let's see how all of this builds as we apply our new visual alphabet and Ohm's law to read a real functioning multi-part circuit system. Take a look at this setup. Right here, we have three distinct resistors connected one after the other. In a series connection exactly like this one, our invisible river is forced to take one single continuous path through every single resistor joined end to end. There are no branching streams here. Every single electron that leaves the battery must pass through resistor 1, then resistor 2, and finally resistor 3.
Logically tracing the journey through this series circuit, we find a few undeniable truths. First, because there is literally only one path, the current never changes. It's completely constant at every single point. However, the total push from the battery, the total voltage, well, that gets divided up. Each successive obstacle in the path takes a little bite out of the total potential difference. So, the total voltage, V, is equal to V1 plus V2 plus V3. And when we plug Ohm's law into that reality, we get the equation V equals I times R1 plus I times R2 plus I times R3.
Now, because the current I is exactly the same in every part of that equation, we can just factor it right out. This allows us to confidently conclude that in a series circuit, finding the equivalent resistance is incredibly simple. You literally just add up the individual resistances. A 1 ohm, a 2 ohm, and a 3 ohm resistor in series simply act as one giant 6 ohm barricade to our invisible river. Which ultimately brings us to a massive real-world dilemma. If adding components in a single series path continually increases the total resistance, dropping the current further and further, and dividing up the voltage, how does your house actually work? I mean, why is it that turning on your high-resistance microwave doesn't instantly dim all your lights or completely shut down your refrigerator? Well, that actually requires a completely different architectural layout for our invisible river, one where the streams branch out. And that fascinating parallel solution is exactly what we will be exploring next time on The Explainer. Until then, keep questioning the world around you.